This is lecture 16. Today we'll be talking about isomers. Isomers is referring to different shapes or structures that molecules can have. We're actually going to start by talking about organic chemistry. So what is organic chemistry? So it's a one-year course that we teach here at BYU, or it's actually 2 semester-long courses. But organic chemistry specifically is the study of carbon-containing compounds, especially the compounds that have carbon-carbon bonds or carbon-hydrogen bonds. Now, why am I bringing this up? Well, because most of the molecules we deal with in chemistry are organic. These tend to be these long chain carbon groups that have a bunch of other molecules sticking off of them. And so this is a good place to talk, or the good type of molecule to talk about, the organic molecule, while we're talking about isomers. So we can draw a Lewis structure for a organic compound like this, where we have a bunch of carbons attached, we have a bunch of hydrogens attached to each of those. But this type of Lewis structure actually gets a little unwieldy, especially as we go to bigger and bigger molecules. So we could draw it like this, or we could write it out in some sort of molecular formula or condensed structure. And so those are both useful, but more often we will draw our molecules with what's called line structure. And we'll start using this line structure a lot more as we go on. And you'll see as we talk about bigger molecules, it becomes really useful. So the way this line structure works is that every end in this, or every bend, so every end or kink or bend is a carbon atom. So here, each of these spots would be carbon, and then each of these carbons also has some hydrogen. But in line structure, hydrogens are implied. They're implied because they tend to be all over the place. They tend to be very numerous, and they tend to be in very consistent places. So for example, with carbon, we're going to imply, or we're going to assume that carbon is always going to form 4 bonds. And so if this carbon has a single bond to that carbon, we can then assume that there are 3 hydrogens surrounding that carbon. And then with this carbon right here, it's singly bonded to 2 other carbons, which that takes up 2 bonds, and it has to have 2 more, so the other 2 will be 2 hydrogens. So we're going to start using this line structure a lot. So let me show you some more complicated molecules that we can draw using line structure. So this one here in the middle, this is caffeine, which everyone ingests on a fairly regular basis. Even if you avoid caffeinated beverages, you still get a little of this from different plants and also from chocolate. We have Tylenol over here, also known as acetaminophen. And over here we have a nasal spray, Nasonex. And you can see all of these are big structures. And so if we put all of the carbons and hydrogens in these, it would quickly get out of control. But we need to be able to recognize both the implied atoms and the ones that are kind of written but kind of hidden. So for example, if we wanted to figure out how many carbons are in acetaminophen, you'd need to be able to look at this line structure and figure that out. So the number here is, I see a kink here, 1 here, 1 here, 1 here, 1 here, 1 here. Let's see if we move through, there's another kink here, and then there's an end right here. So each of those is going to be a carbon. So there'll be 1, 2, 3, 4, 5, 6, 7, 8 carbons in this molecule. I can also ask you to look at something like caffeine here and ask you how many hydrogens are in that caffeine. And you'd have to be able to count it. So generally, if a hydrogen is on something like an oxygen or a nitrogen, we'll actually draw that out. So for example, if I look over here at the Nasonite structure, you'll see that I've got an oxygen here with a hydrogen. On acetaminophen, I have a hydrogen on this nitrogen. But we don't draw the hydrogens bonded to carbon. So the first thing we have to do is figure out where carbon is, and then figure out how many hydrogens are in each carbon. So on caffeine, I have 1 end here, 1 here. I actually have a carbon here, and one here, where these bends are. You have one here, 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 and here. So now let's count the hydrogens on each of those. Well, on this end, it's got one bond to this nitrogen, so it's going to need 3 more. So it's going to need 3 hydrogens here. How about this carbon? It's got one bond to that nitrogen, one to that one, double bonded O, so it's full. So there's not any secret hydrogens here. This carbon is the same story. It's got 4 bonds that are clearly labeled, so no hydrogens. This one down here is going to be similar to the other end carbon. So any end carbons are going to have 1, 2, 3 hydrogens. I'm counting 1, 2, 3 of those end carbons. We've also got a carbon right here, but it's got a bond there, 2 going down. So this carbon has 4 bonds, so no hydrogens. This carbon also has 4 bonds, so no hydrogens. This one right here has 1, 2, 3 bonds, so it's going to have 1 hydrogen. So in total, we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens on caffeine. All right, so these structures like this, they're very common, and they are what we call hydrocarbons. So any molecule that has hydrogen in it and carbon is a hydrocarbon molecule. So let's give you some names of these, and then once we get through a lot of these structures, we can talk about how these structures can differ and give us our isomers. First term I'm going to give you here is an alkane. So an alkane is a hydrocarbon that has no carbon-carbon double bonds. So all the carbon-carbon bonds are single bonds. If there was a double bond in here, we would call that an alkene. So right here I'm showing a carbon chain with a lot of double bonds, but an alkene can also have just a single double bond. However, if anywhere in your hydrocarbon you have a triple bond, then you're actually going to have to call that an alkyne. So there's a hierarchy here. If you have any triple bonds, it's going to be an alkyne. If you have no triple bonds, but you have a double bond or more than one double bond, it'll be an alkene. And then if you have only single bonds, that's your alkane. And as you can see with this alkyne, we have a little bit of a branch thing going on here. Our carbon chain is branching. So I'm also going to introduce this adjective branched chain. So this adjective means that if you have a molecule with a long carbon chain and you have branches on it, it's a branched molecule. It's pretty straightforward. One other set of terms I'm going to give you here is saturated and unsaturated. So if we have an alkane, something with a bunch of carbon-carbon single bonds, we're going to say that's a saturated hydrocarbon. Saturated means no double bonds or triple bonds. So our alkenes and alkynes are then going to be our unsaturated hydrocarbons. So anytime you have a double or triple bond, you're unsaturated. What that means is the atoms in the molecule are bonding to each other instead of bonding to hydrogen. So it's not saturated with hydrogen, it's unsaturated. All right, so now we've talked a bit about structure. Now we are a bit more ready to talk about isomers. So let's talk about isomers in gasoline. So whenever you go to fill up your tank, you'll notice an octane rating. Right here I have the structure of octane. You should be able to look at this and say I have 1, 2, 3, 4, 5, 6, 7, 8 carbons, and then also be able to count the hydrogens on here. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 hydrogens on there. All right, but a funny thing about gasoline is it actually doesn't contain very much octane. The thing we're actually looking at when we're measuring octane levels is this molecule, which has 1, 2, 3, 4, 5, 6, 7, 8 carbons, just like octane. It has 1, 2, 3, 4, 5, 6, 7, 8, 9, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 hydrogens on it. So it has a very similar, or it has the same empirical formula as octane, but this guy is actually called 2,2,4-trimethylpentane, which is a bit of a mouthful. But since it has the same formula, we just kind of fudge the words there. But these two molecules right here are what are known as isomers of one another. They have the same chemical formula, but different structure. Their atoms are attached in different ways. You can think of this as Legos. If I grab a handful of Legos, there's a lot of different structures I can make out of that one handful of Legos. Similarly with isomers, we can have these different isomers. And so this 2,2,4-trimethylpentane is known colloquially as isooctane. So what we're really measuring in our octane levels is the amount of isooctane and actually the amount of this N-heptane. So hep means 7. So we've got 1, 2, 3, 4, 5, 6, 7 carbons in heptane. All right, but let's take a closer look at these octane isomers. So here I have them again. These are one specific type of isomers. Specifically, they're constitutional isomers. So they have the same formula, but different connections. And this different arrangement of atoms can have actually very significant impacts on their physical properties. So for example, I'll show you the density and melting point and boiling point of both of these. And what you'll notice is this more branched guy has a lower density than the linear structure. The linear structure has a melting point of -57 degrees Celsius. So octane is very often a liquid, even at low temperatures. But the branched structure, the isooctane, its melting point is actually 50 degrees less than that. So even at -105 degrees, this is still going to be a liquid, whereas the octane will be frozen solid. And the boiling point for the isooctane is also a bit lower than the boiling point for octane. So these structural isomers or constitutional isomers have very different properties. Let's practice with this idea for a little bit. I'm going to give you an eye clicker quiz, and I want you to tell me which of these following molecules are constitutional isomers of octane. So for this, right, you're going to have to count the number of carbons and the number of hydrogens. Go ahead and pause the video and try and solve all of these, and then we'll go through it. All right, let's start with number 1 here. How many carbons do we have? We have 1, 2, 3, 4, 5, 6, 7, 8 carbons. How many hydrogens? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So here we have 8 carbons, 18 hydrogens. So yes, this is a constitutional isomer of octane. So this next one, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. So that is going to be a no. It has a different number of carbons, so it's got a different formula. It's not an isomer. This next one, we have 1, 2, 3, 4, 5, 6, 7, 8 carbons. That's a good start. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 hydrogens. So yes, this has 8 carbons, 18 hydrogens. So it's another structural isomer. Number 4, we have 1, 2, 3, 4, 5, 6, 7, 8 carbons. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 hydrogens. So yes, another isomer. Here we have 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. That's a no, not an isomer. So for structural isomer, you have to have the same number of all the molecules, but then the position of all of them is all mixed up so that it's a different molecule. All right, so that's our constitutional isomers. Now let's go into a different type of isomer, a somewhat more complex type of isomer. This is our stereoisomer. And in this type of isomer, you have the same formula, you have the same connectivity of all the atoms, but they're just pointing in different directions. Now, the simplest type of stereoisomer, or the simplest to understand, I think, is probably cis and trans isomers. These are what are called diastereomers. Dia meaning 2, but really diastereomers can have multiple conformers. And cis and trans are a subset of the diastereomer type isomers. So cis and trans, all these mean is with cis, you have identical groups on the same side or similar groups on the same side, and trans, you have them opposite of each other. And both of these are referring to a double bond, carbon-carbon double bond. So with a cis, right here, we have a CH3 group on this side and a CH3 group on this side. You'll notice they're both on the same side. The molecule forms kind of a C shape. That's how I kind of remember cis. For trans, these similar groups are on opposite sides of the double bonds. And just like the transcontinental railroad goes across the United States, a trans structure goes across the double bond, whereas the cis is on the same side. So this is one type of diastereomer. Another type is conformers. So right here I'm showing a very simple depiction of different conformers. So these are two pictures of 6-member carbon rings. These aren't the 6-member rings with all the double bonds in the middle. These are 6-member rings with a bunch of hydrogens on them. So it's all single bonds in the middle. And so a 6-member ring, it actually has to, each atom wants to have a tetrahedron conformation around it. And so it can achieve that either by having this chair conformer, where one side's pointing down, one side's pointing up, or it can have this boat conformer, where actually both sides are pointing out. So this is just a simple example of a conformational isomer, but actually every protein in your body has multiple conformational isomers, and generally it's the one that the proteins adopt in your in the solutions in your cells that gives it its function. And if a protein adopts a different conformer, it actually loses its function and stops behaving properly. And then you get problems like Alzheimer's. So even though these are all still connected the same way and we're just kind of flip-flopping atoms, still has dramatic effect on functionality. There's one last type of stereoisomer known as the enantiomer, which is where you have mirror images of molecules. So we'll get into enantiomers in a sec, but first let's hang out with the cis-trans guys for a little bit. So here I am showing two different molecules of 1,2-difluoroethene. Notice we call it ene here at the end because of that double bond. This is an alkene. But here on one of these isomers, we have both of the fluorines on top of the double bond, and on one we have one on top and one below. So this one where they're both on the same side, this is our cis conformation. When they're on opposite sides, this is our trans conformation. So in both of these molecules, the CF bonds are very polar and the CH bonds are not polar. However, these molecules differ in polarity. So I'm going to ask you a question here. This will be an iClicker quiz. Which of these isomers is polar? Are they both polar? Is the cis one polar, the trans polar, or neither? Go ahead and pause the video and figure it out. All right, let's talk about this. So in the trans conformation, we have this polar bond right here. So the dipole is pointing from the carbon through the fluorine. In this other one, we have carbon going through the fluorine. So we have two dipoles in here, but they're actually pointing in opposite directions. So the trans conformation is not polar. But in the cis conformation, we have a dipole pointing from the partial positive in the carbon through the partial negative in the fluorine. And then we have another with the other carbon-fluorine bond. And while these aren't pointing in the same direction, they're also not pointing in opposite directions. So we get a net dipole pointing up through this molecule. So in this case, the cis isomer is polar, whereas the trans is not. So you can see this just simple flip in positioning of things gives us a change in the physical property. Now, in this case, we're looking at things that are identical to one another. But we can also say that one group is cis to another group. So if we have like a long chain coming off of here, a long carbon chain, and on this side we have maybe a carbon ring, we could say the ring and the chain are cis to each other. Or if we have a chain coming down and a ring going up, then we could say they're trans to each other. So this cis-trans verbiage can also be used for things that aren't completely identical. Let me show you some more examples of where cis-trans conformations are actually really significant. And this is in the fats that we eat. So we all eat fats. These are vital for energy production and for other processes in the body. Now, you might have heard of trans fats, unsaturated fats, and saturated fats. So all a fat is a long carbon chain with an acid group on the end. So this is a carboxylic acid, so that's COOH. But we're really going to worry about the carbon chain. In normal unsaturated fats that occur in nature, these are all actually cis, or at least the vast majority of them are. So they're cis, which means they're actually going to have a bend in their carbon chain. So the carbon's going to come up and be, the chains on either side of this double bond are going to be cis to one another. It's going to result in this bent structure. Because of this bent structure, the molecules can't stack on top of each other super well. And if you have more than one double bond, so if you have a poly unsaturated fat, where you have multiple double bonds in there, it gets even harder. So these little kinks in the chain give these unsaturated fats a low density and a low melting point. Now with a saturated fat, where you have no double bonds, you're just going to have a long chain. And these long chains actually can stack on top of each other really well. So when you mix these cis unsaturated fats with these saturated fats, these cis unsaturated fats will kind of break up the saturated ones, give you lower density, and it'll make it easier for your body to burn through them. However, when you get trans fats, which have these double bonds, but the carbon chains are trans to one another, the carbon chain can actually still maintain its linear structure. So when you have these guys together, you actually get a really high density and high melting point. And these can stack fairly easily with our saturated fats. And so your body doesn't super know what to do with these. It actually doesn't have a mechanism for breaking them down, but they're really good for storing. It's really easy to store these. So your body will see these and will say, I don't know what to do with this super high density thing. I'll just shove it into a fat cell or into an artery. And so your trans fats here, because they can stack well and your body can't really break them down, are very unhealthy for you. So this is a really simple way where just this simple bend, the direction of the bend, makes a huge impact on your overall health. So if you didn't know, you shouldn't eat trans fats. You should avoid them a lot. Okay, let me give you an iClicker quiz for the cis-trans thing, or at least another iClicker quiz. This is a molecule known as amberin. It's found in ambergris, which is secreted from the intestines of a sperm whale. So what happens is if a sperm whale eats something like a squid or a jellyfish, something that irritates its intestines will make this mucus sac around the irritant, and then it'll poop it out. And this used to be used, this molecule and other ingredients in ambergris used to be used in perfumes. This is nothing that I learned from any science class or anything like that. I actually learned all of this information from the cartoon Bob's Burgers. But it's actually all accurate. But anyways, this molecule, amberin, I want you to tell me, is it possible to have a cis-trans isomer for this molecule? Go ahead and pause here and try and figure that out. All right, so if you're going to have a cis-trans isomer, you have to have a double bond. This molecule has a double bond right here in the middle, and it has these big groups on either side. So right now, this big group on the right is trans to this big group on the left. Let me move this molecule over here. And you'll notice we also have this conformer where the big group on the right and the big group on the left can be cis to each other. Now you'll notice the shape of this molecule is pretty different. So yes, there can be a cis-trans isomer here. We also have this other double bond, but we actually can't have a cis-trans isomer here because it just has two hydrogens on the other end. And if you switch the places of those two hydrogens, the molecule still looks the same. All right, so that's cis-trans isomers. That's a part of diastereomers. Let's go into our last group of isomers here. This is enantiomers. So enantiomers are fun because everything's connected in the same way. But in this case, the best way to describe it is if you have a mirror image of an object or the molecule, and you can't superimpose the mirror image over the original image, then you have what's called an enantiomer. So for example, if I put a flask or just a glass cup in front of a mirror, the mirror image will look identical. If I put my left hand in front of a mirror, I would get an image that looks like my right hand. If I take my left hand and right hand and try and put them on top of each other, they actually don't superimpose. Let me give you an example of a molecule that does this. So right here, I have a molecule. I have carbon bound to hydrogen, fluorine, bromine, and chlorine. This is CHBrClF, so a big long molecule. And right here, I have its mirror image. So I've got a mirror right here. Let me take this mirror image though. I'm going to rotate the fluorine so that it's facing backwards, just like in the original molecule. So here is the original, or the mirror image just rotated. So now you'll notice I've got hydrogen sticking up and fluorine sticking to the left, just like in the original molecule. But now in the mirror image, with this dashed line indicating that chlorine is going into the page, with this dark line, I'm indicating bromine's coming out. That's the opposite of our original molecule where bromine's going into the page and chlorine's coming out. So there's actually no way to orient this molecule right here so that it will look exactly the same as the original. There are, however, molecules where if you take the mirror image and rotate it around, you can actually get a molecule that looks exactly like the original. So if you have a mirror image that's not superimposable, that's called an enantiomer. So these two molecules are enantiomers of one another. And this is what we call a chiral compound or a chiral molecule. So a chiral molecule has an enantiomer. Whereas this molecule down here, the CHBr2Cl, is not chiral. Its mirror image can actually be rotated to look the exact same. So its mirror image is superimposable on itself. Okay, that seems really complex, and it is, but it's actually not too bad to figure this out, to determine if a molecule is chiral, if it's going to have an enantiomer. So the way you're going to figure this out is you're going to look for a stereocenter. If a molecule has a stereocenter anywhere in it, it's then a chiral molecule. And these stereocenters are found by looking for carbon that's bonded in 4 non-identical ways. So for example, these two molecules down here are enantiomers of each other. And they have one chiral carbon. It's denoted with this asterisk. So let's look at this carbon. So this carbon right here is bound once to a hydrogen. The second bond is to this complicated hydrocarbon up here, right? The third bond takes us around this ring, and the fourth bond takes us around the ring in the other way. Okay, if the third and fourth bonds are both taking us around the ring, how can we say this is a stereocenter? Well, because if I take the right path around the ring, I'm going to run into this double bonded oxygen first. But if I take the left path, I'll run into stuff that looks different. I'll run into this double bonded carbon system. And yes, I will run into all the same features if I walk long enough, but I'll run into the features in a different order. So if I have a ring, and if I go one way around it, I'll run into the features in a different order than if I go in the left direction or the other path, then that's a different, non-identical way of binding. So then these are mirror images of each other that are not superimposable. Enantiomers are actually very important in life. So sometimes they have very similar physical properties, but often they have very different physical properties. So for example, these two molecules are both oils. The one on the left, though, is the oil found in caraway seeds, It's kind of a, not necessarily a bitter, but kind of a blanche tasting oil. Whereas the molecule on the right is spearmint oil, also found in spearmint gum. It's very minty, has a very different taste and effect from caraway. So these have very different physical properties. Another really weird thing about chiral compounds is that they'll actually rotate light. What that means is if you have light coming in and it interacts with a chiral compound, it'll actually twist and spin. And the weird thing is the opposite enantiomers will actually spin the light in opposite directions. One will spin it in a clockwise manner, the other in a counterclockwise manner. This isn't a very well understood phenomenon at all. We don't have a great physics explanation for what's going on yet. But this is a characteristic that all chiral compounds share. And all chiral compounds generally react different with with other chiral molecules. So for example, if I had another chiral molecule, it might come in and react with just spearmint oil, not caraway. All right, let's keep going with this. So chiral compounds are actually super important also in the pharmaceutical industry. Most pharmaceuticals, most drugs that you take are actually chiral compounds. And usually one of the enantiomers serves a specific function, whereas the other enantiomer does not serve that function. We have some molecules, like this shown down here on the left. This one shown on the left is what's known as Ritalin. You might have heard of this. It's used for ADD and ADHD as a medication to help people focus. But its enantiomer is actually an antidepressant. So its enantiomer has no effect on ADHD, and the Ritalin form has no real effect on depression. So in these molecules, though, we actually have two stereocenters each. Remember, in this case, we're looking for carbons that are bonded in non-identical ways. So it actually has two here. And since there's two chiral centers, each of these chiral centers has or can have a flipped image. So there's actually, in this case, 4 different enantiomers. And if there were 3 chiral centers, there would be 2 times 3, or sorry, 2 to the 3rd power, or 8 different enantiomers. So if I take this image right here on the right and rotate it, try and superimpose it over here, then these two bottom connections would actually be facing out of the screen, whereas in Ritalin they're facing into the screen. I'll give you another example here, ibuprofen. Ibuprofen is actually a unique one where both enantiomers serve similar functions, but one enantiomer, the S-ibuprofen, is much more active than the R form. So if you take the R form, you don't notice much. If you take just the S form, you'll notice significant pain reduction. So where in this molecule is our chiral center? So you'll have to be able to do things like this. So you'll want to go through actually every individual carbon in here and ask, is it bonded in 4 unique ways? So right here, this first carbon, it has 3 hydrogens attached to it. It's not going to be that because each hydrogen is identical. We have this other CH3 group. It's also not going to be identical. So you're getting a pattern of CH3 groups. None of them are going to be chiral. Let's look at this carbon right here. It's got a hydrogen in one place, then it's got this long chain, but then it's got 2 CH3s that it's attached to. Those CH3s are identical, so that's not chiral. Here we have a CH2. This carbon's bonded to 2 hydrogens. Those hydrogens are identical, so it's not going to be a stereocenter. Right here in this ring system, all of these carbons are engaged in a double bond. A double bond immediately eliminates these as being potentially chiral. So none of these are chiral. So for this carbon up here, the one in the COOH, you'll have to be able to recognize that that is double bonded to one of those oxygens to eliminate that carbon as chiral. So then we just have this carbon right here. It's attached to one hydrogen, one CH3, one carboxylic acid, and one extended chain system. So this carbon is our chiral center. Let me give you some practice with this. Up here, I've got 5 molecules. Go ahead and try and find the chiral center in each of these. And if you want, you can pause after I go over the results. Go ahead and pause now and try it. All right, so what we're going to want to do is look at every carbon in here one at a time to figure out if it's chiral. So I'm going to start with my CH3s because those are easiest. I can eliminate all the CH3s as non-chiral. They've each got 3 hydrogens. That's not are non-identicals. Those are identical bonds. We can also eliminate the CH2 because it's bonded to 2 hydrogens. So now we're left with these 2 CHs. Let's start with the left one. This CH over here, it's got a hydrogen, it's got this long extended chain, but then it's got 2 CH3s, which are not identical, or which are identical, so that one's not chiral. Now we got this CH, so it's got a hydrogen here, a 2 carbon chain, a 1 carbon chain, and a 3 carbon chain. So this carbon actually is chiral. So we have 1 stereocenter in that. Next, let's move on to this big green guy. We can immediately eliminate the CH3, all the CH2s, and we can eliminate these as CHs because they have a double bond between them. The only one we need to ask about is this carbon right here. It has a single hydrogen, it has a CH3 group, and then it's got this ring. If I go to the right, I'm going to run into that double bond after my first carbon there. Whereas if I go around the other way, I'm going to have to go through 1, 2, 3, 4 carbons before I reach the double bond. So it's not an identical arrangement there. So we have another chiral center there. Next molecule, we have a CH2, we can eliminate that. CH3, we can eliminate that. We have the carboxylic acid here, the C double bond O, single bond to an O that's bonded to the hydrogen. It's got a double bond, so we can eliminate that. So we're just worried about the central carbon. It's bound to a hydrogen, a 2 carbon chain, a carboxylic acid, and an NH2 group. So it's got 1 chiral center. Let's look at D now. In this molecule, it looks like every carbon is in a double bond somewhere. And so none of these are going to be chiral. Last molecule. Okay, in a big system like this, sometimes you'll find there's no chiral centers, sometimes you'll find a few. So let's go through all of these. We're going to eliminate our CH2s and our CH3s right away. We can eliminate this carbon because it's got a double bond. So let's do just our CHs that are in here. So this carbon hydrogen, or this carbon right here has a hydrogen. It has a CH3, then it's got a ring. If I go to the right on the ring, I run into this branch. If I go to the left, I have to go all the way around before I run into the branch. So that will be chiral. How about this CH? Well, it's got a bunch of branches, it's got a hydrogen, and then it's got a ring where you're going to get different features. So that'll be chiral as well. And then this CH has a hydrogen, has a CH3, has a 2 carbon chain, and this big long thing. So it'll be chiral as well. So in this last molecule, we'll have 3 chiral molecules. Let's go back to our ambergris molecule, amberin. And I want you to count on it. How many chiral molecules, or how many chiral centers do you see in this molecule? Go ahead and pause the video and figure it out. Okay, in this one, you're still going to want to go through every individual carbon. Now, if you're good at line structures, you can quickly eliminate some of these. So for example, these end carbons, these are always going to be CH3s. So we know that none of these end carbons that we're seeing out here are going to be chiral for this end. We also know anywhere we have a double bond, it's not going to be chiral. Now in these rings, each of these corners is a carbon. And this is not one of those rings that has a bunch of double bonds. It has all single bonds. So we have to look at all the carbons here. So this top carbon, well, it's going to have 2 hydrogens, so we can eliminate that. So anytime there's a point with just 2 bonds, that's also going to have 2 hydrogens, so we can eliminate all those spots. What about right here? Well, this has 2 CH3 groups attached, so it's not going to be there. So now let's look at this carbon right here. Well, it's attached to 1 ring, and I'll get a very different structure if I go one way around it, or I'll run into the features in a different order if I go one way around it than the other. And the same is true for the other ring. So we have one chiral center here. Now let's look at this carbon. We've again got this ring, or these two rings. I'm going to run into different features in different orders if I take them. And then I have this hydrogen, so that's another chiral center. Let's look at the next carbon. Well, we've got a long chain up here. We've also got an implied hydrogen, and we've got a ring system where we're going to run into things differently in different directions. So there's another chiral center. Let's look at this carbon. Well, we've got a CH3, we've got an OH, and we've got a ring system where we're going to run into the features in different orders. So there's another chiral center. Work our way up here, right here. Got a carbon with just two carbon bonds, so it's a CH2, CH2. We can eliminate those. Nothing here because of the double bond. We've got a CH3 up here. Right here we have a CH2. We've got a CH2. So now let's look at carbons in this ring. Right here, we've got a carbon attached to a long chain and a hydrogen and a ring that looks different in different directions. So we have another chiral center there. How about this carbon? Now it's attached to two CH3s. We got a bunch of CH2s out here and a double bond system. So I'm counting 5 chiral centers in that molecule. If you got that wrong, it's actually super easy to miss these. So that's why I say you want to go through every individual carbon. If you try and take a shortcut and rush through the molecule, you're going to miss a chiral center. You're going to miss the problem, right? So make sure you try and look for every individual carbon and ask how it's doing. All right, so in summary, we went over a bunch of different types of isomers, right? We went over these constitutional or structural isomers where we have the same formula, we just have everything attached in different ways. So there's some further breakdown in constitutional isomers. You don't need to know these breakdowns. Nobody really uses these terms very often. And when they do, most scientists have to just look them up. But you do need to understand constitutional isomers, same formula, different attachments. And then you have your stereoisomers, where you have the same formula, same attachments, just different orientations in space. So we have our enantiomers, where we have our mirror images of each other that are non-superimposable. Then we have our diastereomers. And our diastereomers are broken down into conformers, where these are literally just the molecules moving around. And often conformers can change from one conformer to the other without any type of chemical reaction. Usually if it's put in a different solution, or you change the temperature or something, your molecule will just kind of shift around to get comfortable. So you can get different conformers without a chemical reaction. Cis trans isomers, though, you will need some chemical reaction because it can't rotate around this double bond. So it's stuck in either the cis or trans isomers. So with that, let's leave you with one last eye clicker question. Down here I have 2 molecules. These are both found in apples. They both contribute to apple flavor and aroma. And I want you to look at these molecules and tell me, are they identical constitutional isomers, diastereomers, enantiomers, or are they completely different molecules? Or in other words, they have different molecular formulas. Go ahead and pause the video right now and try and figure that out. All right, so first thing, let's figure out if they have the same formula. They both have 2 oxygens. That's pretty easy to see. Let's see if they have the same number of carbons. I'm counting 1, 2, 3, 4, 5, 6, 7 carbons in one molecule, and 1, 2, 3, 4, 5, 6, 7 carbons in the other molecule. Okay, so same number of oxygens, same number of carbons. Let's count hydrogens. Counting 1, 2, 3, none right there. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 hydrogens on the left. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, none right there. 10, 11, 12, 13, 14 hydrogens on the right. So we have the same formula for both of them. So if we have the same formula, we want to make sure really fast that they are not the same structure. Because sometimes you'll see molecules and I'll ask you what type of isomers are these, and they're not actually isomers, they're the same thing. So let's look for a feature that we can look at. So in the left molecule, we see we have this double bonded oxygen with a single bonded oxygen on the right, and on the left, we only have a single carbon. Let's find this same structure if we can in the other molecule. So we have a double bonded oxygen and single bonded oxygen on the right, but this time on the left, we have this long chain. So the chain looks different in these two molecules. So these are going to be isomers for sure, but since the atoms are attached in different places, that's going to tell us they're constitutional isomers. All right. If you have any questions about that, let me know. These two molecules, one of these has a stereocenter. The one on the right has a stereocenter, but the one on the left doesn't. Generally, if it's a good clue to figure out if you're looking at a chiral molecule with an enantiomer, is I'll usually be indicating that one of the bonds is either going into the paper or coming out. And so that's often a good hint. It's not always going to be the case, so you still need to look for each chiral center or each carbon and see if it's a chiral center. And then if it was going to be a diastereomer, then you'd be looking at cis-trans conformations generally. There you'd be looking for double bonds between carbons. All right, if you have any questions about any of that, feel free to let me know.